Hi, everybody. We have here like a live presentation of Peter Behroozi, who's, well, I guess you're, well, doing vision analysis of the universe. I guess, you know, that's fun of me. All right, welcome.
Great.
Yeah.
So maybe one of the folks in the audience here can let me know if there are questions over the chat.
I'll do that.
Also, people can feel free to shout out. So great. I'm an astronomer. I work at the University of Arizona. I also work at the National Astronomical Observatory of Japan. And I'm here to tell you about an MCMC algorithm for very, very high dimensional spaces. So this talk will be super informal, and so please feel free to shout out if you have questions or want something defined. It'd actually be nice to get some feedback from the audience. I know it's really hard when it's virtual like this, but if folks can just put in the chat, do you already know what MCMCs are, or should I explain that? And that would be helpful.
I think that would be good. Just
yeah.
Give the breadth to the audience.
Give the breadth to the audience. Okay, great. Yeah, so I'll do that. And so right now I'll edit my slides and include more of an intro to MCMCs. Great. Okay. So what do I do? Why am I interested? Why am I here? So I'm an astronomer, and as you've probably heard, we've recently launched a new space telescope, James Webb. At the University of Arizona, we did a lot of design work on James Webb. So the near-infrared camera, as well as the mid-infrared instrument, were both designed by folks at the University of Arizona. And the pictures that you've been seeing coming out on the news, for example, this image of 5 interacting galaxies, this image of the phantom galaxy, these were all produced by cameras built by folks at the University of Arizona. So we're very happy about the success of James Webb. My job, I'm a theorist. I don't build cameras. And so I want to understand, why do galaxies look the way that they do like this, and understand the physics behind what makes galaxies form and evolve. There's one problem with this, which is that running a simulation of galaxy formation from first principles is impossible. And so I just want to give you a sense very briefly of why that is and what we can do about it. So we understand of the fundamental forces in nature. We understand gravity pretty well. And so if we start running a simulation of gravity in the very early universe, then different codes will basically agree on the same result. And so if I start this over at the beginning, in the very early universe, the matter is all sort of spread out homogeneously with a couple of density variations. Over time, gravity will amplify those density variations so that overdense regions will pull in matter from their surroundings and form this filamentary-like structure. And when two filaments cross, those are the densest regions of the universe, and those are where things like galaxies form. The problem with sort of running a galaxy formation simulation comes as soon as you start to go beyond gravity to the other forces, E and M, as well as the strong and weak nuclear forces, which are responsible for fusion in stars. So as soon as you start to turn on the processes for star formation, like radiative cooling of gas across the universe, which will cause it to condense and form dense regions, which will form stars, and then the stars will grow and some of them will explode as supernovae. The problem comes that we don't really understand how all that physics fits together. And so what I'll show you now is 5 state-of-the-art galaxy simulations, which all start from the same initial conditions, all have the same distribution of matter in the universe, which is shown by these sort of 5 blue blobs here. And what you're looking at is a big chunk of the universe, enough for about 10,000 galaxies or so. And what will show up in red is a temperature map of the universe. And so what you'll start to see is, as each of these simulations run, you'll see the temperature of the gas around galaxies heat up, because what will happen is gas will cool and form stars, and some of those stars will explode as supernovae. They'll send out shock waves and will heat up the gas in their surroundings. So if I just run this, you can already see differences where one simulation starts these explosions much earlier than the others. But then the explosions take different forms in the different simulations, and they all sort of propagate in very different ways because of our lack of understanding of how the detailed physics propagates out to larger and larger scales. And so if I just pause this here, you can see vast differences between these simulations. And the sort of other aspect of this is that this is all on a log scale. It's not even on a linear scale. So even slight differences would be a disaster. And so what you see here is just an absolute catastrophe of a lack of knowledge of what happens in the universe as soon as you put in star formation. Okay.
So, question.
Great.
Question. Is it fully understood, or we need really tiny space and time resolution to resolve it?
Great. So we understand the quantum mechanics quite well, but there are huge scale issues. And so that's exactly it. So if a supernova explodes, right, in a galaxy, that will dump in energy on the scale of a light second, but that will send out a shock front that will propagate to a distance of 1 million light years. And so if you divide those two, you get a ratio of about 1 trillion in one dimension. If you run a 3-dimensional simulation, that's 10 to the 36 resolution elements that you would need to resolve a single galaxy. And you would also need another factor of 1 trillion because you need the time-stepping resolution to match the spatial resolution. And so you end up with just a simulated galaxy of order of 10 to the 48 floating point operations. And now you have tens of thousands of galaxies to simulate, right? And so it's just an unimaginable problem for today's computers or computers in the next 10 years to be able to solve this thing.
Right.
Okay. So what can we do instead? How can I even sit up here and talk about galaxy formation? So what I do instead is a very data-driven approach. So instead of trying to simulate galaxies on the sort of atomic level, or as far down in resolution as we can, I try to ask then, what must the relationship be between galaxies and the matter distribution to form the universe that we see today? Okay, so the summary of how that works is we start with a gravity-only simulation, which tells us where all the matter in the universe is clustering. And we try to model the relationship between galaxies, which I've represented by this vector G here, and the distribution of matter in the universe, how fast that distribution is changing, this rho dot here, and then the age of the universe. And we don't know what this function looks like. So what we do is we put in a flexible fitting function. So if you think about a neural network as a flexible fitting function or a bunch of splines, we don't know necessarily what are the physics that sets this, but we want to understand what the universe is telling us about the galaxy matter connection. And so any guess for what this relationship looks like lets us populate a gravity-only simulation, which tells us where the matter is, with things that look like galaxies. So we build a mock universe. And then we ask, does that mock universe look anything like the real thing? So we observe the mock universe in the same way as the past sort of few decades of astronomy and sort of reproduce all the work of thousands of astronomers and ask if they were living in this mock universe, how similar is it to the real thing? And the answer is, for your first guess, not similar at all, because you don't know where to start. But then you iterate, you guess and check many times. The fancy word for that is, of course, MCMC, until you recover what are the distribution of galaxy matter connections that match what the real universe is telling us. And the key there is not just, you don't just want the single best fitting one, but you want the entire range of galaxy matter connections, because you want always to know uncertainties on your result. You always want to know, for a given hypothesis for how galaxies form physically, is that within the range of what's permitted, as opposed to does it look like the best fit solution or not? So as astronomers, we're always deeply caring about what are the errors, what are the uncertainties, and that's why we end up using MCMCs for this approach, because we want to explore the full range of possibilities for how do galaxies fit in the universe in terms of the matter distribution. So let me pause here and ask for if there are any questions so far.
So the big one probably is, I see a time term there that suggests that you're training an ODE of some sort that adds matter correction to your gravity-only like static time series.
Yes.
But it's just, you know, it's called stochastic ODE or PDE, whatever.
Yeah.
Because it's is that right?
Yeah, and so in practice, we model the differential terms, like the star formation rate of galaxies, and so then we can integrate that over time for properties like the total stellar mass or the colors of galaxies, which depend on the sort of star formation history that a galaxy has had.
Okay, so you'll get interpretable parameters as a result.
That's exactly right. And so I've not specified what's in this vector G, but typically what we do is we ask for interpretable parameters like the star formation rate of a galaxy so that we can then integrate that through some other physical model where we understand how do stars change colors as they age and explode and so on. Great. And so what comes out of this is a lot of galaxies. So here's just a fly-through of one of these universes that we generate in a quadrillion times the speed of light. And so the point here is to say that we really are trying to simulate the entire universe. This is to sort of generate this piece. We generated properties for 2 billion galaxies. And so we really are trying to model everything that astronomers would see or will see with present and future telescopes. And then compare all that information, not only sort of counts of galaxies, but statistics like spatial clustering and so on, with the real universe to figure out how close we are to the real thing.
Actually, a question on the call.
Yeah.
Do you have to model the biases of telescopes and measurement mechanisms?
Absolutely. And so that's exactly why we do this sort of forward modeling to the observed space. And so we include either the same selection effects, they're called, when you don't see every galaxy or you don't have the same likelihood of seeing every galaxy in the same way, or in cases where the systematics are not known, the selection effects are not known, we have to include nuisance parameters to account for the range of uncertainties in what those selection effects might be. Great question. And so the summary of that is that if you don't take that into account, of course, you don't have a consistent way of combining data across multiple different telescopes, because each one will have its own selection effects, its own biases. And so then if you're not combining the information self-consistently, you don't know how to interpret the result. Okay. Any other questions up to this point? Okay, so I want to show one plot from the paper where we did this, which is both a triumph and a failure. So on the vertical axis, I have here universes generated and observed per second. On the horizontal axis is the number of processors that we use at the Edison supercomputer at LBNL. And then the dots here are sort of our achieved performance in terms of universes generated per second versus number of processors. And so the triumph is that we achieved strong scaling to over 100,000 processors. And there's a lot of fun stories about this. For example, so that we didn't melt the disk systems when we loaded up all the data from the N-body, the gravity-only simulations, there was actually a mini BitTorrent-like system involved so that all the processors could share with each other instead of just all pulling from disk. Anyhow, so the triumph is, of course, that, yeah, it's hard to build a system that scales this well. But the failing is, why did we even need to go to 100,000 processors in the first place? So I mentioned that we have to generate properties for a lot of galaxies, and yes, that will take a lot of computational time. But the reason why we needed to go to such large numbers is that all the MCMC algorithms that were available that we tried were really inefficient at exploring the distribution of parameters that matched observations. And so we really had to waste a lot of time in the MCMC algorithms to be able to converge on what the universe was telling us about galaxy formation. And so out of this frustration with current MCMC algorithms grew the motivation to figure out new pieces for how do we understand what is the range of galaxy matter connections for my own research that match what the real universe is telling us. Okay. So I've just sort of given a little bit of motivation here from my own research. I'm interested in modeling how galaxies form, and that's actually a fairly low dimensional problem compared to what other folks are dealing with in astronomy and beyond. So we have, say, a 50 to 100 dimensions in our fitting functions. Other folks who are training deep neural networks, depending on whether you're building a large language model or driverless cars, or even just something simple to interpret a temperature or time series. You might have anywhere from 100 to 100 trillion dimensions that you're working with in terms of the weights and biases of the network. And what people typically will do is they'll train a best fit solution. But that doesn't necessarily tell you about what are the range of solutions that would do a decent job with your training set. And so when you encounter something new that's outside of your training set, you have no idea whether your best fit solution is going to tell you something realistic, or whether the range of possibilities that match your training set would just give you very divergent answers. And so this becomes critical when you're interested in understanding reliability and robustness. For astronomy, it means we want to understand our errors. For the real world, you want to understand, are my estimates of the situation around me in my car reasonable? Or for a medical image, you want to know uncertainties, or is this something new? And so there are many cases where you care about the robustness and reliability, where it'd be nice to know what are the range of neural networks as opposed to just the best fit model that work. There are a couple of other examples in astronomy. So confused source recovery, that's when you have a telescope that can see very deep, but not very high resolution. And so you have potentially a lot of galaxies or stars overlapping in your field of view, and you want to figure out what are the colors and brightnesses of each one. And also cases like this one, where you want to run a simulation where you match the properties of the Milky Way galaxy and other nearby galaxies like Andromeda. And so you then need to figure out what are the initial conditions of somewhere north of 1 billion particles so that they all collapse in the right way via gravity to form structures like the surrounding neighborhood. Yeah. But the main point is that no MCMC algorithm, and there's sort of other similar ones, nested sampling, there's another one, normalizing flows. None of these work really well for extremely high dimensions. And so I want to sort of explain, first motivate what are MCMCs, get a little bit of background, but then explain why don't they work for very high dimensions, and then what can we do to make them work in the future. Okay, so a little bit of background. MCMCs, what are they? I mentioned them many times already. It's a way of going from observations to a range of allowed parameters in your physical model. And so the thought is you have some observations that you want to reproduce, like an image or a time series, and you have some model with some parameters over here that lets you generate data that look like your observations. And then you have some loss function or a likelihood function that evaluates the similarity between your model and your data for a given choice of parameters. And MCMC algorithms, as well as other similar techniques, then try to explore the range of allowed parameters that are consistent with your observations. Okay, and so the way that sort of very simple algorithms work, they're like random walks with rejections. And so if, for example, my range of allowed parameters looked like this blue circle here, and I started from some point here, if I took a random walk and ended up outside at a place that didn't look like my observations, I could reject that. If I randomly took a step inside, then I could keep that step. And over time, as I tabulated the points that I kept rather than the points that got rejected, I would end up with a distribution of points that looks like my allowed parameter space. Okay, so that's sort of the 1-minute introduction to what MCMCs do. What makes a good MCMC algorithm or a bad MCMC algorithm or a good nested sampling or a good normalizing flow and so on, there is a function called the transition probability density function that determines how I jump from one point in my parameter space to another point in my parameter space. Okay, so I'm going to skip this math because it's not sort of immediately relevant. And people can ask questions about that later if they're interested about how sort of the general algorithm works. And so the types of methods that many people use, the most common ones are either sort of random walks like this. So you start from a point in parameter space, you pick a random direction, you take a random step in that direction. Another common one in astronomy is the stretch step. So you pick 2 points from your distribution and you sort of scooch along the vector connecting those to have a new trial point over here. And this works for distributions that have funny shapes, like Rosenbach distributions. And there are also more advanced ones, like Hamiltonian Monte Carlo methods. And these are really cool because they make a connection between the likelihood surface or the goodness of fit surface and a physical system. And so the thought here is if you identify the chi-squared value of the model versus the data as a gravitational potential, then you can send a ball rolling in this potential, and so it will sort of orbit around in the likelihood surface and find good places that are all sort of within the range of allowed values. And so this is often what's used if you have more complex problems. We'll see why still this tends to fail as you go to very large dimensionality nonetheless. Okay, so these are the most common ones. There are a billion different MCMC algorithms, and so if you have questions about a particular one, I'm also happy to talk about others. But just for the sake of introduction, these are sort of the three main ones that many people in astronomy use. So now I want to give you some intuition for why are high dimensional spaces so hard to explore with MCMC and other algorithms. Okay, so first bit of intuition is just what is the shape? Where is probability located in high dimensional spaces? If I consider a common distribution like a Gaussian distribution, we can learn some lessons from it that actually transfer to many other generic distributions in high dimensions. So if I just write down a Gaussian distribution, the probability is proportional to the exponential of minus the distance from my origin in this case. If I then ask, what is the distribution of distances from the origin? If I pick a random point from this Gaussian distribution, what is the distribution of distances from the origin? Well, it'll scale like this exponential, fall off, but then I'll have to multiply by the amount of volume at a given distance, or amount of surface area at a given distance. And so the distribution of radii from the origin will look like the surface area of a d-dimensional sphere, so that's r to the d minus 1, times the fall off in the density with distance. Okay, so what have I done? What do I have? I have a piece here that rises super fast as I leave the origin, and then I have a piece here that falls off super fast as I leave the origin. If I multiply those two together, then what happens is that there is a sort of rapid rise and then an equally rapid fall, and the combination of those two gives me this sort of sharp peak as I get to higher and higher dimensions. And just to visualize that, I've shown here just a couple different Gaussian distributions in from 2 to 1,000 dimensions. And what's being shown here is just the range of radii in colors that have similar probabilities to the sort of maximal probability radius. So the yellow here corresponds to the radius of maximum probability, and then the other colors correspond to sort of various fractions of that maximum. And so what you find is for a 2D Gaussian, you have a lot of different radii that are sort of similar in magnitude to the probability of the maximum radius. But as you go to a 10D Gaussian, then that sort of range shrinks. 100-dimensional, it shrinks more, and 1,000-dimensional Gaussian, it shrinks more. So you're left with this very thin shell where all the probability is concentrated because you have such a huge surface area as you go out from the origin. And even though the probability might be much less than at the origin, you have such a huge surface area that compensates. Another way of thinking about this is if you're familiar with central limit theorem arguments for a 1,000-dimensional Gaussian, the distance from the origin, you're sort of summing up 1,000 different independent random variables, or the squares of 1,000 different independent random variables. The more independent random variables that you sum up, then the less variance in their sum that you get, or relative variance, I should say, in the sum that you get. And so that's the same thing. The central limit theorem also says for a generic distribution, the thickness of that distribution will shrink and shrink and shrink. So you're left with all the probability in this very thin shell in high dimensional spaces. Okay. So that's sort of an interesting thing is that there's almost no probability at the center because there's almost no volume at the center of high dimensional distributions. Okay. Next thought is, how do we understand where are independent points located? So the goal of an MCMC or other algorithm is to give independent draws from the posterior distribution of the allowed parameter space. Because if you give correlated draws, you don't get as much information. And so the maximum information comes when you sort of get to an independent point in parameter space. And so as humans, what is the highest dimensional space that we're familiar with? It's actually flavors, right? So if I were to ask you about different colors, you could say like red, green, and blue. You have sensors for those. But humans can tell apart tens of thousands of different flavors. And by flavors, I mean not only sort of which taste buds, but also which smells, what mouthfeel, and so on. And so if I were to ask you about different flavors, you could probably name thousands of different foods that you've had that are all sort of distinct from one another. And if I take two random flavors like coffee and pizza and I ask what's the dot product between those, that's a question of sort of what is the overlap between different flavors, right? So the dot product is formally sort of the lengths of the two vectors times the cosine of the angle between them. And if you ask anyone, oh yeah, like did the pizza you have last night taste like coffee? They'll give you a blank look because that doesn't happen ever, right? And so if I take two random flavor vectors and the dot product of them, that's basically 0. And that gives us the intuition that mathematically, if you take the dot product of two random unit vectors in a high dimensional space, the expectation value of their squared is basically, that dot product squared is basically 0 in a high dimensional space, which means that two random unit vectors are most likely orthogonal. Okay. So to summarize the problem of going from one random location in the probability space, let's call it V1, to another random location, V2, then we need to go from one vector to an orthogonal vector, and the space of probability that connects the two is this very thin shell like this. So this is sort of summarizing the intuition that we have for what is the shape of high dimensional spaces and where are independent vectors in that space located. Okay. So now let me pause here and ask questions again. Anyone has anything?
So is the intuition for this that you only be very different in one dimension or extreme in one dimension to be on the shell or orthogonal? And as you have more dimensions, the odds of that is very high.
Right. That's exactly right. And so another sort of more human analogy to this is, let's say you have 1,000 different dimensions for how you measure humans, like maybe, I know, height and weight and intelligence and location or wherever. And there's an average across the human race for all of these, but it's impossible to find a human that's average in every single way, right? And so you always have differences in some way or another that add up to put you away from the average in some location out here, as opposed to finding everyone that's sort of average in every single way.
Right, makes sense.
Okay. And so to make the analogy here again to humans, you'd want to move from one human, which has sort of differences in some ways from the average, to another random human, which will have completely orthogonal differences from the average. And then you need to sort of migrate through the space of humanity to get from one to the other. So then we can understand why it's hard with current algorithms to travel from V1 to V2, right? This location here to this location here. With random walks, also known as Metropolis Hastings, you pick a sort of random direction and you travel in that direction. And the problem is that if you take a large step, then you immediately go off this high likelihood surface, and so you reject the point. And so what you have to do is you have to take really tiny steps, and that means you have to really slowly diffuse through this very thin surface until you get from one point to an independent point over here. So the physical analogy with taking a random rock is like diffusion, and so that also gives you a sense of why does it take a long time for getting from one point to another point along sort of a very thin surface like this. Okay, so it ends up scaling that you need of order the number of dimensions of evaluations of the likelihood function to even step from V1 to V2 to sort of diffuse your way along the high dimensional surface like this. Other sort of random walk type steps. So even if you sort of stretch or use other points in the surface as sort of directions to travel into, it turns out not to be any better. In some cases, like the MCMC, so the Goodman-Weir stretch step, it ends up being a worse constant in front of the dimensionality. The better approaches then don't diffuse, but they keep a velocity and they stick with it. So a Hamiltonian MC gives you a much better order of dimensionality here. So order of dimensionality to the quarter power for a Gaussian distribution. The penalty is that you have the time that it takes to compute the gradient of the likelihood function in d dimensions. And so in some cases, you're lucky. And so if you write everything in JAX, for example, or use another autodiff technique, sometimes this time can be just the same order of computing the likelihood function in the first place. Sometimes you're unlucky and you just have to do it numerically, in which case you get sort of a range of scaling with dimensionality of d to the 1/4 to d to the 5/4. Okay. But the same point is clear, is that you have to sort of creep along this very thin surface to be able to travel from one point to another point. Okay. And this figure sort of summarizes that. There are other techniques, Mela, which is also using the gradient of the likelihood function to sort of adjust where you are. All of these scale with dimensionality to some power. Okay, can we do better? Because when you're going up to 100 trillion dimensions, you don't want dimensionality to some power. You want, at best, log of the dimensionality to hit you.
Okay, question.
Yeah.
Why do you want to travel from one point to another point? Is it that either local optima, or is it this region is accepted, and then you want to find another accepted region?
Great. Great. So with an MCMC, the goal is to find the full distribution of allowed.
All of them.
Exactly. And so you want a fair sample of everything. So instead of, say, just sampling people around San Francisco, you want to sample people in San Francisco and Tokyo and London and South Africa and Thailand, right? So you want to sample fairly from all the places in the world, as opposed to just sort of gathering lots of information about a local region. Okay. Great. And so the question we should always ask, along with why is it so hard, is should it be so hard? Right? This is also like very important whenever you have a hard problem. Should it be so hard? And I think the answer in this case is no, because if you imagine that you could search in a given direction until you found another point on this sort of thin probability shell, then that would let you cut through vast regions of empty space like this and not have to creep along this sort of thin shell of where most of the probability is. And that might let you achieve much better scaling with dimensionality. And so just as a teaser then of what the performance is like, I'm showing here a plot of how many evaluations of the likelihood function you need to reach an independent point in the posterior distribution. So to get a fair sample or a fair random sample of the posterior distribution, how many samples of the likelihood function or evaluations of the likelihood functions you need. And so it's bad if you need a lot. That means you're slow. And it's good if you don't need a lot. That means you're fast. And so here are the three different techniques that I mentioned. I'm happy to talk about how others like nested sampling or normalizing flows fit into this. They all sort of scale with some power of dimensionality. The new technique that I'll talk about, adaptive searchlight, for a Gaussian distribution, it's O of 1 to get to very high dimensionality. So I've shown here, even for a million dimensions, the performance is no different from 5 dimensions. And for generic distributions beyond Gaussian distributions, we can show that the scaling is the log of the number of dimensions as opposed to any power of the number of dimensions. Okay, so the performance can be much, much better. What drives this performance? Why is it so good compared to the techniques that have gone before? So the thought here is that the transition step, instead of being a random walk, could just be a search algorithm. Okay, so let's say I'm starting here at one point of the probability distribution, and then I'm ending up over here at another point. What kind of information would I need to get from one point to an independent point? If I think about a light ray traveling, I could parameterize the location of that light ray as my initial position, plus some unit vector times a scaling factor like this. So if I take a line through this high dimensional space in a random direction that I've chosen, then I can ask, what does the goodness of fit function, like the chi-squared function, look like as I move along this line? And that's some one-dimensional function. So it's a one-dimensional slice through this very high-dimensional space. And that then means I can search along this one dimension until I find a goodness of fit that is the same as the goodness of fit that I started out with. Okay, so for experts with MCMCs, you always want to sort of be able to find different goodness of fits. And so I'm happy to answer sort of later why this is a good idea and how we can sort of get ergodicity nonetheless. But just for the sake of explaining the very basic idea, if you know your likelihood where you start, you can very easily search for the same likelihood where you end up. And you can use a root finding algorithm to do this without having to evaluate lots of points along this one-dimensional space. So for example, if you just take the one-dimensional gradient as well as the double derivative, you can ask sort of where would a parabola, if I just had a sort of a parabolic approximation, you could ask sort of where would I guess the parabola would cross, and so you could sort of skip and then skip to where the right answer is, as opposed to sort of having to evaluate lots of points to get here. Okay, and this is what gives us scaling like the log of, yeah.
You need the gradient though.
You need the gradient in one dimension, and so you can evaluate that numerically in O of 1. It doesn't scale with the number of dimensions. So yeah, so whether or not you have autodiff, it doesn't matter because it's just the same order of computation. In this case, it doesn't matter. Great. And so the thought here is then, now I can reduce the problem to a one-dimensional problem. If I pick a good direction, I can go in that good direction and end up on a completely different spot. And this is where the log of dimensionality scaling comes in. So if I have a generic function, generic chi-squared function, if my root finding algorithm is basically binary division of intervals, then the amount of time that it takes me to transition from this point to this point depends on the ratio of the thickness of where I'm landing to the overall distance that I'm traveling here. And so if I take the log of that ratio, that's basically how many binary subdivisions I would need to start from a distance that's this long and then find out where I would need to go in the sort of short target space where I want to end up. Okay, so I mentioned before that we can connect many different MCMC algorithms to sort of physical processes. So a random walk is like diffusing through space. A Hamiltonian MCMC is like taking gravitational orbits through a potential well. Searchlight, this new algorithm, is like black body radiation from a surface. And so if you make the connection with optics, in particular Hamiltonian optics, then you see a lot of properties that make this, make the proofs that it works as an MCMC algorithm a lot simpler. So for example, things like reversibility. A key feature of MCMC algorithms is, many MCMC algorithms, I should say, is reversibility. And so if you have light coming from some point, so if you glue a flashlight, or a searchlight in this case, to one point in your probability distribution, and you shine out light rays and you ask sort of, what is the intensity of light where they fall? That scales as the distance to the power 1 minus the number of dimensions. And that's reversible. So if I have another sort of flashlight that I glue, or searchlight that I glue onto this location, then the intensity of light that reaches over here will be exactly the same. It'll just scale in the same way with distance. And so a fixed luminosity over here will correspond to a fixed sort of received luminous intensity over here, and the same thing with light coming here and ending up over here. So there's some very nice physical properties that translate into mathematical properties of an MCMC that make this whole system work. There's another really fun property of this type of algorithm, which relates to another common failing of MCMC techniques. So something that's really hard for MCMCs is if you have sort of multiple disjoint probability surfaces. So if your probability distribution is lumpy and you have multiple modes, then typical algorithms will sort of creep along one of these modes, and only in sort of very, very rare circumstances will they have enough sort of random chance to jump over to a different node, and then they'll be stuck in a different mode like this for a long time. And so they're very inefficient at exploring whenever you have potential barriers or likelihood barriers between different parts of your probability space. If you think about this instead as an optical system where these likelihood contours have an optical depth, what that means is that a light ray shining from one point in the probability space can intersect with a boundary here, but then with some probability it can pass right through, and then you can search for the next route or for the next route. And so what happens is if you have a partial transparency to the probability surfaces, you can very easily transition across multiple modes and bounce around and efficiently sample different modes of your distribution without having to wait a long time to sort of jump over a potential barrier.
Okay,
yeah.
These are hard visualization.
Yeah.
Let me see if I can rephrase what you're saying. So you start at some point, whatever it is.
Yeah.
You shoot in an arbitrary direction, not pick a dimension, some vector, the random vector, it sounds like. Okay.
Yeah.
And then you're looking for the point with the same likelihood.
Yes.
I guess, well, why same and not really any other number?
Great. So this gets to the sort of a question at the heart of MCMC algorithms. What do you need to sort of explore the distribution well? And so you not only need reversibility, but you also need ergodicity. So you need to be able to explore also different likelihoods. Okay. So the algorithm, as I described it, searches for the same likelihood, and you want to also be able to explore different likelihoods. But that's okay because there's a trick that's also used with Hamiltonian Monte Carlo methods where you augment the dimensionality of your space. Okay, so here's how it works. With Hamiltonian Monte Carlo methods, you not only have a position vector, but you also have a velocity vector. And you have some sort of distribution of allowed velocities, and you have sort of a likelihood or chi-squared, if you will, associated with choosing a given velocity. And so what that means is just like kinetic plus potential energy is conserved, your likelihood can slosh back and forth between kinetic and potential energy, meaning your position space likelihood and your velocity space likelihood. So even though the total is conserved, total kinetic plus potential energy, you can still sample different potential energies in your orbit, like throughout your orbit, right? And so the same process applies here, is that we can augment the, I mean, it sounds like a bad idea. Like, why are you making a high dimensional problem even more high dimensional? But it turns out to be a good thing. So you augment the space with a complementary space where you place some likelihood function. And so you can write down your sort of original space X, your complementary space V. The combined likelihood function is a product of two separable likelihood functions. And so what that means is that if your new likelihood is the same as your old likelihood in this higher dimensional space, you can nonetheless look at or travel to different likelihoods in your original space, because now you have some of the likelihood captured in this complementary space. So you can let likelihood sort of slosh back and forth between the spaces. So even though you're looking for a point that's the same likelihood in the higher dimensional space, it'll be a different likelihood in your original space.
So I get why this is, you're not going to be stuck in your likelihood.
Yes.
Is there a bias introduced in your sampling process?
Yes.
Okay.
So the bias is introduced both in Hamiltonian Monte Carlo and in this technique is that there will be some correlation between your initial likelihood and your final likelihood from this.
Yeah.
And so the answer to that is that in Hamiltonian Monte Carlo, you're sort of stuck with just the same number of dimensions in your complementary space as your initial space. With this technique, you're actually not. And so what I did for this, this plot here is I actually just had 10 times the number of dimensions in my complementary space. And that doesn't hurt me because the log of the number of dimensions isn't worse.
Yeah.
If you have 10 times more, it's just like +1, right? Or in this case, it doesn't matter how many dimensions I have. And so that then lets me explore very efficiently in the likelihood variable as well as in the position space variables.
Okay. So okay, now back to the original thing. You have random point in a parameter space.
Yep.
You pick a random vector, you should along find another thing that's equally likely. You use or roof factor, like moving method, something. For that you need the full gradient, right?
You still don't need
using it along the line, but you need a gradient along.
So once you've picked a direction, then it becomes a completely one-dimensional problem. And so as long as you travel along a one-dimensional path, then you only care about the derivative along that path as opposed to outside, because you'll never travel outside that path. And so there's sort of, it becomes a restricted problem where, for example, you're traveling along a string in the space now, and you still have the same sort of, along the direction of your travel, you still have sort of forces pushing you one way or the other. But you never need to know the derivatives in orthogonal directions to your travel.
But now, computational cost-wise, I still need the full derivative code.
No.
I'm not going to be compiling it.
No.
That vector.
No, so you don't, because you just need to numerically evaluate going a little bit forward or backward along the same path, right? So if I have a one-dimensional function, I don't need derivatives in other directions to find a new root for that one-dimensional function, or if I've restricted myself to one-dimensional space. So I'm really just like a bead sliding along a string to find a new spot. And I never need to know anything more than just the function plus or minus a little bit along my string. And so that means to evaluate a derivative, I just need my current position plus a little bit to evaluate a numerical derivative, as opposed to taking a full gradient and then dotting it with my direction.
Oh, wait. You could use the gradient code.
Yes.
What you're actually, I think, using is, imagine you're running some piece of software.
Yeah.
That's your case. And you're running it on the two nearby points.
Exactly.
Instead of running the JAX derivative.
Exactly.
And, well, you don't have to worry about their numerical instabilities. You have a different known numerical instability of the
Yes.
You can't go too far away from that point.
Yes.
Okay, so less dependence on having a derivative or adjoint or whatnot.
Exactly.
Oh, so
Exactly. Yeah. So you don't need the software in JAX. If you have it already in JAX and it's fast to compute the derivative, and that gives you better numerical properties than computing a numerical derivative, which it does in many cases, then you can use the JAX derivative or the JAX gradient. But if you don't have that, if you just have some giant piece of code that you don't want to convert into JAX, that's also okay, because you can just evaluate it numerically at different points and still be okay.
Okay, and then where does the log come from?
Yeah, the log comes from the fact that the sort of target width of the distribution is thinning with the number of dimensions. And so because that gets thinner and thinner, if you think about how search algorithms scale, like if you have a binary search algorithm, the larger the dynamic range between the distance you have to travel in that search and sort of your target tolerance, then the more sort of iterations you have to do.
Okay. It's binary search.
But the binary search is sort of the very most basic thing you can do, and gives you the most confidence that you'll end up with a log of D scaling. So in certain cases, if your function looks smooth in certain ways,
yeah, you can just jump.
You can just jump, and you can get O of 1. But the generic case is a binary search will work regardless, and you get log of the number of dimensions in the worst case.
Okay, so log is one vector shot.
Yeah.
But I didn't hear anything about the number of such shots you need to resolve this space.
Great. And so the number of such shots is independent of dimensionality, right? So the thought there is that you know that you need to go to an orthogonal location. And so you actually then know sort of the directions that are good to search in, because you don't want to sort of search in a direction that would sort of land you too close. But you already have a prior on which directions are good directions to go and which directions are not, right? Because if you know already that you need to end up basically X distance from the origin and it needs to be an orthogonal vector, then it already sort of tells you where you have to sort of search to end up.
Oh, so you just go,
right.
You go in the normal direction all the way.
Yeah, and so for Gaussian distribution, sort of the geometry is the same with the number of dimensions, and sort of where you have to end up is the same, basically, because you still have to end up at an orthogonal location. And so it's just that you win by not having to creep along the surface. You can just sort of shoot directly toward where you think you might need to go and end up close to that location.
So now, yeah, this is all just a bunch of concepts all at the same time.
Yeah.
Now,
great.
The other option would be just jump. Like I think Metropolis Hastings is just jump randomly.
Yeah.
Why is this seems more controlled jump?
Yes.
What does the control give you? I mean, it's orthogonal that you get that right.
Great. So the control jump, yeah, same like the controlled jump is just that you land in the right spot, right? So if you just sort of jump off a cliff, right, you just don't know where you're going to land. But if you sort of jump with the right momentum to end up on the opposite side of the canyon, right, that's where you want to be, as opposed to sort of just like blindly jumping in places. And so the search lets you sort of land in the right spot, as opposed to landing plus or minus a meter or more from the right spot, in which case you would be toast.
So why not just jump as far as you can, opposite side of the space,
yeah,
where everything is because it's on the surface. Yeah, why don't you just take an orthogonal vector and just go in that direction all the way?
Because if you go too far, right, then you're again off this sort of high likelihood space, right?
Got it. You want to be far, so orthogonal, and as far as you can.
Yeah.
But not as far as you can, same likelihood.
Yes, exactly.
That means you're still in the reasonable likelihood space, but you can find a reasonable likelihood region, and then you can start jumping around.
Exactly.
That helps.
Great. Yeah. So you want to end up over here as opposed to like in a much worse goodness of fit, or a much better goodness of fit, because a much better goodness of fit, actually, there's very little volume around that area.
Okay. And I have a question. Make sure this is audible. Yeah. How does this method handle regions of high curvature in the posterior? Is it the same way that HMC struggles with divergence in those kind of regions?
Great. And the answer is it doesn't care, because it doesn't have to stay along sort of high regions of curvature to find a different location. And so if you have sort of high curvature in one region, what that means is that some of your rays will sort of hit nearby and won't travel very far, but then there's still a decent chance that some rays will break out of that region and travel to larger distances. So what will happen is if you have sort of a lot of high curvature regions, then the constant in front of the log D will change, because now you sort of need more samples to be able to break out of one of those regions. But once you break out, then you go really far.
Okay. Thanks.
Great.
Oh, and Patrick has a question. Can you say, unmute yourself?
Hey, can you hear me?
Yes.
Yeah, cool. So one thing I don't understand here is why you're losing this order descaling from evaluating the probability density. Because if I think about just like, say, just the simplest thing of a Gaussian in D dimensions, and just evaluating that costs me O of D, just to simply touch every dimension, right? And so, like, you know, that's the exact cost of doing, say, the finite differencing, or even if you want to do this via autodiff and do like a JVP or something like that, it would be the same thing. I don't understand why that's been lost.
Great. And so the reason that's been lost is I've expressed this in terms of likelihood evaluations as opposed to including the cost of that likelihood evaluation. So you're absolutely right that the cost of evaluating the likelihood function sort of scales with the number of dimensions just linearly. And so that sort of same scaling applies to everything. So something like a Hamiltonian MC that scales as d to the 1/4 power, if you include the cost of evaluating the likelihood function, not just the number of likelihood evaluations, then you would have order of d to the 5/4 to d to the, 9/4, right?
And so, isn't that the evaluation of the gradient though in HMC? Right, you wrote d to the 1/4 a cost of the gradient evaluation. And that gradient evaluation is the PDF essentially.
Yes. So again, the summary there is that this number here is just the number of likelihood evaluations, and so you'd have to multiply this then by the order of the likelihood evaluation to get the total computational cost. And so O of 1 here, or O of log d here, is really O of d, or d log d, for the total computational cost.
Okay. So my understanding is that it's gone from d to the 5/4 from HMC down to d log d for this approach.
Yes.
Okay, cool. That makes sense. And then follow-up question, you said you do a line search, and I'm curious what kind of line search, what are the details that sort of fill in that blank?
Great, okay. So the simplest thing to do is really just a line search. So again, the connection to optical systems is you would have some kind of opening angle that you send out your search rays, and that would sort of illuminate some other part of the surface like this. But if you ask sort of what kinds of different search paths, so now this is we're at the end of the hour, so I'm going to sort of talk a little bit about what's next, because you're asking about sort of optimal search paths. Light travels in a straight line, but there's no reason that space-time can't be curved. And so you can also think of ways to curve light paths in your space, potentially to get a better exploration. So in other words, if you have sort of lots of local curvature in your space from the likelihood function, if your geometry of space-time ends up being something sensible, then you might be able to sort of come out of those regions more easily. So there's a lot of open questions with this type of algorithm. So just to sort of segue into this part, what's next? What's next is that I realize this is probably bigger than one person like myself can do. And so I'd like to talk with folks to understand their problems, what they're working on, because there are a lot of unknowns here. So what is an optimal search algorithm for many different types of distributions? Patrick's question, like, what are optimal search paths? So right now, there's straight lines, but you can think of how should we curve light paths to make things better, or even making an analogy to fluid dynamics. If you think about incompressible fluid flows, that also gives you a way of transiting from one point in a space to another. So if you solve Navier-Stokes in 1,000 dimensions, that might also be a useful path to take from one point in parameter space to another. Other things like how do you tune the algorithm as you learn sort of more about the probability space that you're in, or how to best deal with boundaries. And so all this sort of goes into the last point here, is that I'd love to talk with everyone here to understand what kinds of problems you're working on, to understand if there's a partnership that's interesting to folks that we can move forward to develop the algorithm to better suit what you're working on.
Thank you, by the way, for the answer.
Great.
So are there any other questions in the call? All right, well, in that case, yeah, thank you very much. Fantastic.
Great.
Thank you.
Great. Thanks, everyone. And so my email address is here if you want to write any questions or find me. Yeah.
That's perfect.
Great.
Oh, and I'll ask one last question. Is there a GitHub link, or is it still in development?
So this is still in development. And so we have things that work on Gaussians, obviously, and I'm just now trying on neural networks to see what happens.
Okay.
It didn't crash yet, which is good. But within the next couple of months, there'll be a paper and a GitHub link. And so I'm happy to share that with folks if they send me an email to express their interest.
Well, fantastic. Yeah, thank you.
Great.